Hello everyone, welcome to Hope's class. Today we will look at derivatives. In Unit 1, we talk about the 0 over 0 form in limits and continuity, which led us to the concept of the derivative. A derivative calculates slope of the instantaneous rate of change at a specific point. The derivative of a function f(x) is a new function f prime x, defines the limit below. If the limit exists, here, the h is a small increment. Some people will use the Leibniz notation to express the derivative as dy by dx. Read as dy by dx. This notation means determine the value of the derivative when x is a. Okay, let's look at one example. Consider the equation y is x squared. Sketch the graph and estimate the instantaneous rate of change when x is 1. Here is the graph. We have learned how to find the average rate of change. So we know that the average rate of change between 0 and 1 is 1. When the endpoint approaches to 1, sets from 0 to 0.5, its average rate of change will increase to 1.5. When we're approaching to point 1, 1, we use a derivative formula to find the instantaneous rate of change when x is 1. Substitute x is 1 and h is 0 into the formula, still give you 0 over 0. Don't panic. To solve the 0 over 0, we need to remove the indeterminate form. Okay, second example. Consider the function y is x squared. Use the derivative to calculate the instantaneous rate of change when x is 1. According to the definition, the instantaneous rate of change of f(x) when x is 1 is its derivative at that point. We will substitute f(x plus h) equals to x plus h squared and f(x) is x squared into equations. Expand the bracket and simplify the expression. We can divide by h and let h approaches to 0. Finally, substituting h is 0 and x is 1 into equation, solve for the answer is 2. Conclusion: derivative for f(x) is x squared when x is 1 is 2. Okay, discussion. Limiting existing for a function being continuous does not always mean it's differentiable. The existence of a limit is a minimum requirement. There are 3 conditions for this, which we have already learned. If all conditions are met, combined with 2 other conditions, we get a continuous function. However, even if a function is continuous, we must make sure it changes smoothly. Otherwise, the derivative does not exist at that point. Here are 3 examples for non-differentiable points: corners, cusps, and a vertical tangent. At this point, the function changing sharply. Derivative is a powerful tool, but it's not useful to all situations. There are 6 situations that are non-differentiable. First 3 are discontinuity and non-differentiable. The next 3 examples are continuous and non-differentiable. Our next video is derivative in power function. Thank you. For more information, please search Toronto Teacher Hope in YouTube.